Last time we explored probability kernels, which are a combination of a function and a probability measure. And we saw that they can give us a good general tool to identify conditional expectations of a function of a random variable onto another random variable. Let's make that precise right now. Suppose we have a probability space and two measurable spaces, which are the state spaces of two random variables, x and y. Let mu of xy denote the law of the random vector xy, that is the push forward of the probability measure p to a measure on the product space by xy, and let mu x be the law of x, the push forward of the probability measure p under x. If we can find a probability kernel over these two state spaces such that the joint law of x and y is the product of the law of x with that kernel. Remember that we defined products of probability measures and probability kernels last time. If we can find such a Q, then for any L1 function of the product space with respect to the joint law of x and y, the conditional expectation of that function f of xy given x equals the value little x can be computed as the integral of f at xy against the probability kernel q of x and dy. So we get contributions to x from both the function and from the kernel, integrating out the y variable. This is the generalization of the result that motivated our discussion of probability kernels in the first place, where we saw that we could describe the conditional expectation in this form if x and y have a joint density in terms of the conditional density, where the conditional density is defined roughly by the joint density of x and y is equal to the marginal density of x times the conditional density. This is the generalization of that, where this q, which we don't know yet exists, plays the more general role of the conditional density of y given x. Now again, just as a reminder, what it means to say that this measure in two variables is the product of this measure and this probability kernel is that the expectation of f at x and y for any such L1 function f is the integral on the outside of the measure mu of the integral on the inside of f at xy q of x dy. Now that is defined usually for functions f that are bounded. But we saw last time that it actually extends all the way to L1 of the appropriate measure. We're going to prove this theorem now. And again, just to remind ourselves what this notation actually means, since it usually is not literally conditional expectation on this event, what we're saying is that the conditional expectation of f at x and y given x, this random variable which is measurable with respect to x and therefore is a function of x, is given by the function g, which is exactly this integral of the function f of two variables against the probability kernel q. Now, in order to show that this statement is true, it suffices by the averaging property to show that for any bounded function of the first variable, x, the expected value of f at xy times h at x, which is a generic bounded function measurable with respect to sigma of x, is equal to the expected value of just g of the random variable x times h at x. So we're going to prove that now. We will show it's true for L1 functions f of the joint law mu of x and y, but to start, we're going to show that it's true for bounded product measurable functions. In that case, if we take this expectation on the left-hand side and use the change of variables theorem, we can write it like this. Now we use the assumption that we made, which is that the joint law here can be written in the form the law of x alone product with this probability kernel Q. And so, using the lemmas that we proved last time about how you integrate against a product of a measure and a probability kernel, and how you integrate against a probability kernel, this integral becomes the integral on the outside over S1 of the single law mu of dx, and on the inside, the integral over S2 of f at x, y, h at x, q at x dy. Now, since we have this product structure here, h of x doesn't depend on the integration variable on the inside, and so we can pull it out of the integral. And therefore, that becomes the integral of h of x mu x of dx times the integral over S2 of f at xy q of x dy. Now, that inside integral is exactly the function g that we're looking for. And so this is just the integral over S1 of h of x times g of x mu x of dx, which by the change of variables theorem is the expectation of h of x times g of x, which is what we wanted to show. So therefore, we've shown that this theorem holds true for bounded product measurable functions f, and now we wish to extend to L1 functions. We'll do that with an appropriate cutoff limit argument, as usual. So if we start with any function f in L1 of the product space with respect to the joint law of x and y, let's do a usual cutoff. Cutoff f when it reaches height n. This is, of course, a bounded function, and it is still measurable. And moreover, since the function f is in L1, this cutoff converges in L1 to the function f that we're cutting off. So by the change of variables theorem, it follows, by definition, that the random variable fn of x and y converges to the random variable f at xy in L1 of the original probability measure. Now remember that conditional expectation is an L1 contraction. And so since fn of x and y converges to f at xy, it follows that the conditional expectation of fn of xy given x converges in L1 to the conditional expectation of f at xy given x. But we also know from the first part of the proof on the previous slide that since fn is a bounded function, this conditional expectation can be computed via this integral against the probability kernel q, and then evaluating the variable x at the random variable capital X. Now what we want is to show that this conditional expectation has a similar formula with f in place of fn, and so what we will do is control the difference between this, that is this, and that desired formula without the cutoff there. If we can show that this goes to 0 in L1 sense, then we will also have that this converges in L1 to this, and therefore those two will be equal, which is what we wanted to show. So, to show that, we just again use the change of variables theorem. Taking the expectation of this overall function of x is the same thing as integrating that difference against the law of x. Now we'll use the triangle inequality to move that absolute value inside. And now we note from our lemmas last time that that is precisely how we integrate against the product of mu x with q. So this last term is equal to the integral of fn minus f against the product measure, mu x times q. Our assumption in the theorem is that this product is the joint law. So that's the integral of fn minus f d mu xy. And one more application of the change of variables theorem says that that is nothing other than the L1 norm of fn of xy minus f of xy in the original measure p. And we know that that goes to 0. Therefore, we have proved our formula for general L1 functions f. So that's what we'd like to do, just like we showed in the case that there's a joint density for our two random variables, where we can then write down a formula for the conditional density. If we can find this Q, if we can divide out the joint law by the marginal law of x and get a probability kernel, that probability kernel will allow us to describe the conditional expectation in exactly this way. So the question is, can we do that? Can we always find a probability kernel so that mu x factors through mu xy with a q? Now, as a first remark, if we can do so, then there will be a unique probability kernel, at least unique up to sets of mu x measure 0. Because as we saw last time, if I had two probability kernels that both satisfy this factorization property, it then follows that the two kernels agree for almost every x, that is, almost every with respect to the law of the random variable x. So on our quest to see if we can always find such a Q, we're going to change the problem slightly, although we'll see in a few minutes that it amounts to the same thing, and ask for the existence of what's called a regular conditional distribution. So we have a similar setup. We have a base probability space, and we have two random variables x and y on that probability space taking values into state spaces. A regular conditional distribution for y given x is a probability kernel over that pair of state spaces with the property that the conditional probability that y is in a set B2 given x can always be calculated as that kernel Q at x and B2. Remember, a kernel is a function in the first variable, a measure in the second. So we're plugging in the measurable set B in the second variable and then evaluating the function variable at the random variable x here in order to get this, which is a random variable measurable with respect to x and therefore is a function of x. We're declaring that it must be a function that looks like that. And just as a reminder, this conditional probability given x here, which is a random variable measurable with respect to x and therefore is a function of x, is just the conditional expectation, orthogonal projection, of the indicator of the event y is in B2 given x. So in that case, another way to say this, since this is a kind of generic bounded function a la Dynkin, is to say that if we have any bounded function h of the second state space, then the conditional expectation of that function h of y given x can always be computed by taking the integral of that function h of y against the probability kernel q of x dy, leaving a function of x which you then evaluate at the random variable x. Now just a word on notation. Some authors prefer to refer to this not as the regular conditional distribution of y given x, but as the regular conditional distribution of y given b. In other words, they index it just by a b here instead of by the event that y is in b. This is largely just a notational choice, since if we can construct one of these guys relative to any x and y, then we could take y to be the identity map on S2 in order to construct the one where you're just interested in conditioning on the sigma field B. Now, at first blush, this looks a lot weaker than what we were asking for on the last slide. We were hoping to find a probability kernel that gives us this factorization property of x, y on one side and x on the other, which, as we saw, if it exists, will mean that we can compute the conditional expectation of f at xy given x in terms of q. Here, we're only computing the conditional expectation of a function of y alone given x, which seems like a different and easier problem to solve. But it turns out that it is not. And here is the proposition. If q is a regular conditional distribution for y given x, then in fact that Q satisfies this stronger factorization property. And therefore there is only one such Q up to law of X null sets. So that is to say, if this holds for functions of y given x, then it also holds with the same probability kernel for functions of x and y given x. And you're going to prove that on your homework. Let me just give you a brief preview of how that argument might start. Suppose that our function f that we're interested in, this more general property, is a tensor product function. It factors in the form a function of x times a function of y. Well, then we can compute the conditional expectation of f at xy given x. By definition, that's the conditional expectation of g at x times h at y given x. And now, one of the basic properties of conditional expectation is the product rule. This is an x measurable function, and therefore we can pull it out. Now, if we have this weaker property which defines regular conditional distribution, this is therefore equal to g at x times the integral of h of y q of x dy, where we're using shorthand to sub in the random variable x for the variable x after the fact. But now we can move this random variable, which is independent of the variable of integration, back inside the integral and see that this is in fact equal to g of x times h of y q of x dy. And this is once again f at x, y in this case, proving that this is true for tensor product functions. So now in order to prove this in general, you need to see how to generalize from tensor product functions to general measurable bounded functions. And that's your homework. For this reason, we might call this proposition a jazzed up version of the pull-out product rule for conditional expectation. Okay, so again, I've given you a definition. Now, I've simplified the definition. At first, we wanted to have this factorization property. Now we want this property here, which looks a little simpler, but in fact we see is equivalent. Either way, the question still stands. Given a pair of random variables, does there exist a regular conditional distribution, which therefore means we have this factorization property and can so express the conditional expectation of a function of x and y given x? The answer is no. There does not always exist a regular conditional distribution. There are nasty enough state spaces that rule out such distributions from existing. However, the answer is yes if the state space of the variable y, not the one you're conditioning on, but the one you're conditioning, is nice enough. Now, nice enough in this case means a standard Borel space, which means a measurable space that is isomorphic to a Borel set over Rd, which actually is the same as a Borel set over R as far as measure isomorphism is concerned. We saw one result last time that required countably generated sigma fields. Well, standard Borel spaces are certainly countably generated because Borel sigma fields over separable metric spaces are countably generated. But this is stronger. In fact, some of the known counterexamples to the existence of regular conditional distributions still have countably generated measurable spaces for the state space for y. We are not going to make any attempts to prove this theorem. It's not very different from other fundamental existence theorems that we've proved. For example, Skorohod's theorem. And in fact, if you look at the detailed proof in the appendix to section 19.5 in Driver's notes, you will see that the non-constructive proof of this result there actually resembles the proof of Skorohod's theorem in several ways. But I don't think it's worth our time to go through the nitty-gritty details of that, when in fact the proof won't give us any further insight into how to construct these regular conditional distributions in the case that they exist. So we're going to content ourselves with a practical understanding of the existence of regular conditional distributions in two settings that mirror the understanding of distributions in undergraduate pre-measure theory probability, the continuous case and the discrete case. Here, we'll actually start with the continuous case because we've already seen a version of it. In fact, it's what motivated the entire discussion of the last two lectures. Suppose that we have two measure spaces, and the measures don't have to be probability measures, just sigma finite measures will be fine here. That is, we're putting sigma finite measures on the two measurable spaces that are the state spaces of our random variables. And suppose we have two random variables on the same probability space, taking values in those two measure spaces. And this is the key here. Suppose that the joint law of x and y, which is a probability measure on the product space, is absolutely continuous with respect to the product of the two sigma finite measures we have there. This is the most general version of what we did with two real-valued random variables having a joint density with respect to Lebesgue measure. Denote that joint density with respect to the measure nu1 times nu2 as rho, and let's let rho x be the marginal density of x. That is, you integrate out the y variable with respect to the nu measure on y, and define, in this context, the conditional density of y given x via the exact same formula that we used before. Then, if we use that conditional density as the density for a probability kernel, in fact, that probability kernel will be a regular conditional distribution for y given x. And the proof of that is almost literally exactly the same as the proof that we went through at the beginning of the last lecture in order to motivate this discussion. If you would like to see the nitty-gritty details, you can look in the appropriate section of driver's notes. So when we have a joint density in this very general sense, that we can find a couple of measures on the state spaces of the random variables so that the joint law of the variables is absolutely continuous with respect to that product measure, then we can construct a regular conditional distribution appropriately, as we did before. And this is something you can imagine actually computing. That is the most prominent case that we will use for regular conditional distributions. But there is another easier case, which in fact will come up in a lot of contexts, at least early on in our discussions of stochastic processes to come in the very near future. And that is the sort of opposite case where the random variables, instead of being jointly continuous in a general sense, are in fact discrete. Suppose that we have two discrete random variables, meaning that we have x and y defined on some probability space with values in two countable state spaces. And just to avoid any unnecessary complications, let's just make those countable state spaces the full spaces of the range. That means that the probability that x is equal to any given element of the state space is always strictly positive. Otherwise, we would throw that x out. And similarly for y. Now, in that case, we can always, in the naive pre-measure theoretic probability sense, compute this number. For any set B in S2, we can compute the conditional probability that y is in B given that x equals x. The probability of blah given that x equals x, since this is a positive probability event, is a new probability measure on the same sigma field, which is the full sigma field in this case. And so by countable additivity, you can compute this just by summing over all elements of B the conditional probability that y equals little y, given that x equals little x. So I claim that it follows from there that this random variable, the conditional probability that y is in B given x, can be computed via a regular conditional distribution Q, this probability kernel here, which is just almost exactly the same formula. Q of x and b is the sum over all y and b of these numbers here. In other words, in the discrete setting, a regular conditional distribution just amounts to finding a function of two variables such that the probability that y equals y given x can be computed as that function q of xy, with x substituted in for the random variable x. And in fact, that function of two variables is nothing other than this, what's sometimes called transition kernel, the probability that y equals y given that x equals x. Now, showing that this simple calculation implies that this holds true is also going to be on your homework as a matter of interpreting the new random variable ideas of conditional probability in terms of the old numerical conditional probability. But I do want to conclude by making a few comments about how very confusing this notation can be. What we're saying here is that the probability that y is equal to a value little y in its range, given x, this random variable, can be computed by taking the probability that y equals y given that x equals little x, which is a function of the non-random variables x and y, and then evaluating that at little x is equal to the random variable capital X, which you might naively try to write as the probability that capital Y equals little y given that capital X equals capital X, which of course is basically meaningless. You would then be drawn to conclude that this is just the probability that y equals little y, which is not true. What we're saying here is that first you compute this function, q of two variables, little x and little y, which is just the probability that y equals little y given that x equals little x. Once you've computed that function, you then substitute in the random variable x for the first variable little x. This is a random function of y. And 3, the result here is that the conditional probability that y is in a set B given x, which is a function of x, can be computed just by summing up these over all y's in the set B. We'll continue our discussions of regular conditional distributions and probability kernels next time as we ramp up towards the definition of Markov processes.